Myself, Sanmugsundaram, Professor Sri Ramakrishna Engineering College. This video is about resonance in RLC series and parallel circuit. The following topics are covered: resonance in series RLC circuit, quality factor, bandwidth and half power frequencies, resonance in parallel RLC circuit. When resonance occurs and what happens when it occurs? Resonance occurs in any circuit that has energy storage elements, at least one inductor and one capacitor. Example, RLC series and parallel circuits. So here L and C are energy storage elements. Under resonance, the total impedance will be equal to the resistance of the circuit, and the maximum power is drawn from the supply. Under resonance, the supply voltage and supply current are in phase. That is, the power factor is unity. So that is, the phase angle between voltage and current is zero. And at resonance, inductance and capacitance, they exchange energy freely. So thereby, sinusoidal oscillations will occur across these elements. Resonance circuits are used in many applications such as selecting the desired station in radio and TV receivers, voltage amplifiers, current amplifiers, and filter circuits. Resonance in series RLC circuit. Resonance is a condition in a circuit in which capacitive and inductive reactances are equal in magnitude and thereby resulting in a pure resistive impedance. It means the resonance occurs when the inductive reactance becomes equal to capacitive reactance and the circuit impedance becomes equal to resistance. At this instant, the net reactance in the circuit will be zero. You see this circuit. So three elements are connected in series R, L and C. And here JXL is the inductive reactance of inductance and minus JXC is the capacitive reactance of capacitance, and VR is the voltage across resistance, and VL is the voltage across inductance, and VC is the voltage across capacitance, and V is the supply voltage, and a variable frequency supply voltage is applied here, and I is the current in the circuit. So the impedance for this circuit is R plus JXL minus JXC, which can be written as R plus J into omega L minus 1 by omega C. So omega L is XL, 1 by omega C is XC. At resonance, the net reactance becomes 0. That is, XL minus XC becomes 0. In other words, we can say that XL will be equal to XC at resonance. And I am calling the resonant frequency as omega R. So therefore at resonance, XL will be omega R into L, and this will be equal to XC, that is 1 by omega RC. So from this, we can get an expression for omega R, which will be equal to 1 by under the root LC, and its unit is radians per second. And from this, we can get the equation for frequency in hertz. So you know the relation between omega R and FR. So omega R is nothing but 2 pi of F. So if you divide this by 2 pi, you will get frequency in hertz. So therefore, FR is 1 by 2 pi under the root LC. So where omega R and FR or resonant frequency, omega r is in radians per second, whereas fr in hertz. Then variation of reactance and impedance with frequency. In this graph, the variation of reactance and impedance is shown here. So we all know that inductive reactance XL is 2 pi f. So with the increase in frequency, the inductive reactance also will increase. So it is a straight line. That indicates that it is linearly increasing with frequency. And whereas capacitive reactance is given by 1 by 2 pi f. It is inversely proportional to frequency. Therefore, at low frequencies, the value is very high. With the increase in frequency, Xc decreases. And you can find that at a particular frequency, both curves meet at this point. It implies that Xc equal to XL at this point, and this frequency we call it as resonant frequency. And as far as impedance is concerned, at low frequency impedance will be more, and as frequency increases the impedance decreases, and the impedance will be minimum and it will be equal to resistance R at resonance, and further increase in frequency impedance of the circuit increases. So at resonant frequency, the magnitude of Z will be equal to the resistance of the circuit, and the power factor is unity. Circuit behaves like a pure resistive circuit. Below FR, so Xc is greater than XL. Therefore, since Xc is greater than XL, the circuit will be more capacitive and the power factor is leading. So you know that when the power factor is leading, the current will lead the voltage by some angle. Coming to the third case, above FR, that is resonant frequency, that is after this, you'll find that XL is greater than XC. Therefore, the circuit behaves more like an inductive circuit and the power factor is lagging. Implies that the current will be lagging the voltage by some angle. Now let us see the impedance phasor diagrams. For frequencies below FR, Xc is greater than XL. Therefore, net reactance XL minus Xc will be negative. So therefore, this vector is drawn pointing downwards, and R is the resistive phasor, and vector addition of these two phasors gives the resultant vector Z, and where phi is the phase angle between R phasor and Z phasor. Coming to the second case at FR, that is resonant frequency, Xc will be equal to XL, both reactants will be equal and they cancel each other, the net impedance becomes equal to R. So therefore, Z will be equal to R. Third case, above FR, XL will be greater than Xc. So therefore, XL minus Xc will be positive. So therefore, this vector is pointing upwards, and this is the resistance, and vector addition of these two phases gives the resultant vector Z. So phi is the phase angle between the resultant vector Z and the resistance. So the phase angle of this circuit is given by tan inverse of reactance part by real part. The reactance part is XL minus XC and the real part is R. Current is given by I is equal to V by Z. So at resonance, the impedance becomes equal to R. Therefore, the maximum current will be flowing at resonant frequency because the impedance is minimum in the circuit only at resonance. So therefore, this current I am calling it as Im, which will be equal to V by R. The variation of magnitude and phase of current with frequency is shown in this figure. So here you find that the current increases with increase in frequency and becomes maximum at resonant frequency. Again, further increase in the frequency, the current decreases. So the current at this point is called as Im, maximum current. So that will be equal to V by R. The current will be only limited by the resistance. So coming to the phase angle, at resonance, the phase angle is 0. Circuit will be behaving like a resistive circuit. But for frequencies below Fr, the circuit behaves like a capacitive circuit. So the circuit will be having leading power factor. So frequencies above Fr, the circuit behaves like an inductive circuit and circuit has lagging power factor. Coming to the quality factor, it is denoted by Q. The sharpness of resonance in a resonance circuit is measured quantitatively by the quality factor Q. This quality factor relates the maximum or peak energy stored in the circuit to the energy dissipated by the circuit per cycle at resonance. It is also regarded as the measure of the energy storage property of a circuit in relation to its energy dissipation property. In the series RLC circuit, the quality factor is given by omega or L by R. And this also will be equal to 1 by omega R C into R. So this expression is in terms of L and R. This is in terms of C and R. If we are going to replace omega R by 1 by under root of LC in this expression, we will get quality factor as 1 by R into under root of LC. Also, the Q factor is defined as the ratio of reactive power of either capacitor or inductor to the average power of the resistor at resonance. For example, for inductive reactance XL at resonance, the Q factor is given by reactive power of inductance divided by real power of resistor, that is I square XL by I square R. I square gets cancelled, so we will get XL by R. XL is nothing but omega R into L. So the quality factor equation is omega R by L. For capacitive reactance Xc at resonance, again Q can be written as reactive power of capacitor divided by real power of resistor, I square Xc divided by I square R. For capacitive reactance Xc at resonance, Q is given as reactive power of capacitance divided by real power of capacitor, that is 1 by omega R C into R. Voltage in a series circuit. We will see the phasor diagram for three cases. One is below Fr. When the frequency is below Fr, circuit will behave like a capacitive circuit. Current will lead the voltage. So therefore, VL minus VC will be negative. So therefore, this phasor is drawn downwards, and this horizontal phasor is VR. The vector addition of these two phasors gives the resultant voltage, which is nothing but the supply voltage in the circuit. And phi is the phase angle between this VR phasor and the resultant vector V. Coming to the next case, when F is equal to Fr, that is at resonant frequency, circuit behaves like a resistive circuit. Voltage and current are in phase. So therefore, the voltage across capacitance and voltage across inductance both will be equal. The magnitude will be equal and they cancel each other. So therefore, the voltage cross resistance is VR. This will be equal to the supply voltage. And coming to the third case, when the frequency is greater than Fr, VL becomes greater than Xc. Therefore, VL minus Vc will be positive. So this phasor is drawn pointing upwards, and VR is the voltage across resistance, and the vector addition of these two phasors gives the resultant vector V. Phi is the phase angle between this voltage across resistance VR and V. Then voltage across the various elements at resonance. Voltage across resistor at resonance. So at resonance, VR will be equal to IR into R, that is current flowing through the resistance multiplied by the resistance. So the current flowing in the circuit is IM. This is the current flowing at resonance. So IM into R. This can be written as where IM is V by R. So V by R into R, this gives us V. So the voltage across the resistor will be equal to the supply voltage. The voltage across inductance at FR. So VL will be equal to IL into XL, the current through the inductor multiplied by XL. So current, since all the elements are connected in series, the current will be same, that is IM. So IM into, whereas XL is written as omega R into L. This further, it can be written as, just to replace IM by V by R, we will get this expression, omega R L into V by R. So here we know that omega R into L by R is nothing but Q. So Q into V. Similarly, the voltage across capacitance at resonant frequency VC is IC into XC. Again, replace IC by IM and XC by 1 by omega RC. Again, replace IM by VM by R. So we get equation as 1 by omega R C R, and in the numerator we get V. So 1 by omega R C R is nothing but Q. So this can be written as Q into V. So if you see these two equations at resonance, both voltages are equal. This also Q into V and this also Q into V. So therefore, at resonant frequency, voltage across inductance will be same as voltage across capacitance. Coming to the effect of frequency variation on voltage across R, L and C. So if you see this curve, so here voltage versus frequency curve, current in the circuit varies like this, increases, becomes maximum value at resonant frequency, and again it reduces with the increase in frequency. The voltage across resistance, since it is nothing but I into R, it follows this curve. So the shape of the curve is similar to the current. So the voltage across resistance increases, becomes maximally at this point, again decreases. So coming to the capacitance, so I told you that initially the reactance will be high, so there will be some voltage at low frequencies. Further, the voltage increases and reaches maximum value, and if further frequencies increase beyond F4, again it decreases. Then coming to the VL, at low frequencies, the voltage across inductance is less, and as frequency is increased, voltage across inductance also increases. At resonance, it becomes maximum, and further increase in frequency, voltage across inductance also reduces. So at this point, we find that both VL and VC are same. In RLC circuit, at resonance, maximum power is drawn from the supply. The resistance is the component which will be consuming power. So the power at resonance is called as PR equal to square of the current at resonance, that is Im square into R, where Im is voltage divided by resistance. So coming to the resonant peak bandwidth and half power frequencies. So let us consider this curve. So it is a current waveform. So it is drawn between current versus frequency. So at low frequencies, the magnitude of current will be less. With the increase in frequency, current increases and becomes maximum value at omega r. Further increase in frequency, the current reduces. So at omega r, the current is maximum and it is written as I max equal to V by R. And here, the two frequencies are marked here as omega 1 and omega 2. So these frequencies are called as half power frequencies. At these frequencies, the current will be equal to I maximum by root 2. That is, 1 by root 2 times this maximum current. And the difference between these two frequencies is called as bandwidth. A range of frequencies between omega 2 and omega 1 is nothing but bandwidth. So omega 2 minus omega 1 will be the bandwidth of the circuit. And here frequencies are called as half power frequencies. That is, at these frequencies, the power drawn by the circuit will be half of the power drawn at resonance. So therefore, the bandwidth represents the range of frequencies for which the power level in the signal is at least half of the maximum power. So the power at omega 1 and omega 2, that is at these 2 points, will be half of the power drawn at resonance, that is PR by 2, that will be equal to Im square R divided by 2. The bandwidth of the circuit is also defined as frequency range between the off power points when I is equal to Im by root 2. So these two are the points where current is equal to Im by root 2. So the frequencies falls between these two frequencies, omega 1 and omega 2, is called as bandwidth. So the bandwidth is given by bandwidth equal to omega 2 minus omega 1. So this will be equal to resonant frequency by Q factor, that is omega R by Q. The bandwidth also can be expressed as, so this omega 2 minus omega 1, which is equal to omega R by Q, this can be written as omega 2 minus omega 1 equal to R by L. We substitute Q is equal to omega R into L by R. So we get omega 2 minus omega 1 as R by L, radians per second. Suppose if you want to get F2 minus F1, so this will be equal to this term divided by 2 pi. So that is R by 2 pi L. Thus, since this is a frequency and unit is hertz, the lowest half power frequencies omega 1 is given by this equation, that is minus R by 2L plus under the root of R by 2L whole square plus 1 by LC. This is in radians per second. And similarly, the upper half power frequency is omega t equal to R by 2L plus under the root of R by 2L whole square plus 1 by LC radians per second. So the difference between the two frequency is, so here we will have a minus sign here, whereas here we have a positive sign. Suppose half power frequency is for Q greater than 1. When Q is very much greater than 1, Q is Q factor. So this term 1 by LC will be very much greater than R by 2L. So therefore, this term can be neglected in this equation. Similarly, this term can be neglected in this equation. So therefore, this frequency omega 1 can be written as minus R by 2L plus under the root of 1 by LC. So we know that 1 by under the root LC is nothing but omega R, and R by 2L is nothing but bandwidth by 2. So bandwidth is, it is R by L. So therefore R by 2L will be bandwidth divided by 2. So therefore this equation can be written as omega R minus omega n equal to bandwidth divided by 2. So further we can write omega 1 as omega R minus bandwidth divided by 2. If you are going to replace this bandwidth by R by L, so we get omega 1 equal to omega R minus R by 2L radians per second. Similarly, this equation can be written as omega 2 minus omega R will be equal to bandwidth by 2. And from this, omega 2 can be written as omega r plus bandwidth by 2. So that is omega 2 minus omega is nothing but bandwidth. And omega r minus omega 1 will be equal to omega 2 minus omega r. So this frequency range and this frequency range will be equal. This difference will be equal to bandwidth by 2. So this is the total bandwidth. So from this point to this point is total. So bandwidth divided by 2 is this portion, and similarly this portion also will be equal to bandwidth by 2. So if you're going to add bandwidth with half of the bandwidth with omega r, you will get omega 2. If you're going to subtract half of the bandwidth from omega r, we will get omega 1. So therefore omega 2 is omega r plus r by 2l radians per second. Conclusions. In series RLC circuit at resonance, the voltages which appear across the reactive components such as L and C can be many times greater than that of the supply. So here voltage magnification take place, and this voltage magnification is called as Q factor. And an RLC circuit accepts maximum current from the source at resonance. For that reason is called an acceptor circuit. So this circuit allows maximum current at resonance. So therefore this circuit is called as acceptor circuit. Coming to the problems. Problem 1. In the circuit below, R is 2 ohms, L is 1 millihenry and C is 0.4 microfarad. A. Find the resonant frequency omega R and half of frequencies omega 1 and omega 2. B. Calculate the quality factor and bandwidth. C. Determine the amplitude of current at omega R, omega 1 and omega 2. D. Calculate the voltage across the elements R, L and C. So from the given data, we have to find all these values. So part A, we have to find out the resonant frequency omega R. It is given by the formula 1 by under root LC. So L is given as 1 millihenry, C is 0.4 microfarad. Substitute the values. Find omega R. It is 50 kilo radians per second. Then the lower half power frequencies omega 1. So use this formula omega 1 equal to minus r by 2l plus under root of r by 2l whole square plus 1 by lc. So all the values are known. Substitute all the values, will get 49 kilo radians per second. Similarly, upper half power frequency omega 2 is r by 2l plus under root of r by 2l whole square plus 1 by lc. Substitute all the values, we get omega 2 as 51 kilo radians per second. Then coming to the bandwidth. So bandwidth is nothing but omega 2 minus omega 1. So we know omega 2 and omega 1, the difference is 2 radians per second. This is bandwidth. Coming to the quality factor, and we know that relationship between quality factor and bandwidth. It is Q is equal to omega r by bandwidth. So omega r is 50 radians per second, that divided by 2. So this will be equal to 25. So quality factor will not be having any unit. Then coming to the current at resonance, the current IRMS will be equal to VRMS by R. But in the circuit, the voltage is given as 20 sine omega t. It is therefore VRMS will be 20 root by under root 2 and R is 2. So this gives us value 7.07 ampere. Similarly, current at omega 1 and omega 2 will be equal to 1 by root 2 times this current, so which will be equal to 5 ampere. Coming to the voltage across the elements R, L and C. So VR is IR into R, the current at resonance multiplied by the resistance. So this gives us 14.14 volts. Voltage across inductance is I into XL, that is I into XL is omega R into L. Substitute all the values, we get voltage as 353.3 volts, and this is the RMS value. So VC is I into XC. This will be equal to I by omega R into C. Substitute all the values. So we get VC as 353.5 volts. So from this we can understand that at resonance BL is same as VC, that is both are same. Their value is 353.5 volts. Coming to the second problem, a circuit having a resistance of 4 ohms with an inductance of zero point 0.5 Henry and a variable capacitance in series is connected across a 100 volt 50 Hz supply. Calculate A, the capacitance required to attain resonance, B, the current at resonance, C, the voltage across the inductance and the capacitance at resonance, D, the power factor of the circuit. So the values given in the problem are resistance is given 4 ohms and inductance is given as zero point 0.5 Henry and supply voltage is given as 100 volts 50 Hz. So let us see how to calculate all these values. To calculate the capacitance at resonance, so here we have to assume that the resonant frequency as 50 Hz. So for resonance to occur 50 Hz, we have to find out the capacitance. So we know that at resonance omega R L will be equal to 1 by omega R C. Omega R is 2 pi Fr. So therefore XL is 2 pi Fr into L. This will be equal to 1 by 2 pi Fr C. So from this find C. So C will be equal to 1 by 2 pi Fr whole square into L. So substitute the values, frequency is 50 and L is 0.1 So we get capacitance value as 20.3 microfarad. Then find current at resonance, omega equal to omega. Current at resonance is given by voltage divided by current because the impedance at resonance will be equal to resistance. 100 by 4 which will be 25 ampere RMS. So whenever you are going to divide an RMS value of voltage by resistance, we'll get RMS current. Voltage across inductance VL. So this is I into XL, that is I into 2 pi Fr into L. Substitute the values, you will get the voltages as 3927 volts. They have similarly voltage across capacitance is VC. VC is I into XC. XC is so 2 pi Fr into C, that is I by 2 pi Fr into C. Substitute all the values, we'll get VC as 3927 volts, 3927 volts RMS. So at resonance, we find that VL is same as VC. But one thing also you should remember, applied voltage is only 100 volts, whereas voltage across inductance and capacitance is very large. So that is 3927 volts. Then finally find the Q factor. Q factor is given by the formula omega R L by R. So omega R is 2 pi Fr into this L and this R. So substitute the values, you will get value as 39.6 500 Hz. If the resonant frequency is 6000 Hz, what is the Q factor? If resistance R equal to 10 ohms, what is the value of inductive reactance at resonance? Calculate the inductance and capacitance of the circuit. So the values given are, bandwidth is given as 500 Hz. So bandwidth of the circuit is given by resonant frequency divided by Q factor. So that is Fr by Q. So here in this problem, the bandwidth and resonant frequency are given in Hertz. Since both are in Hertz, so here resonant frequency we can consider Fr. So this further in turn can be written as Q equal to Fr divided by bandwidth. So Fr, that is resonant frequency, and bandwidth is known, so we can find the quality factor of the circuit, which comes to be around 12. Then you also know that quality factor is omega R L by R. Omega R L is nothing but XL. So that is inductive reactance at resonant frequency. So from this, using this equation, we can find XL. So I can write XL as Q into R. So Q is known, R is also known. So multiply Q with R, we get value as 120 ohms. Next, after knowing XL, we know that XL is equal to omega R into L. So from this equation, we can find inductance. So this further can be written as 2 pi Fr into L. So find inductance L from the formula XL divided by 2 pi Fr. So substitute the values. XL is known and Fr is known. So you will get the value as 3.18 millihenry. And also we know that at resonance Xc equal to XL. So that is Xc is 1 by 2 pi Fr into C. So equate this to 120 ohms. So already we have found out XL. So now Xc also will be same as XL. Therefore equate this to 120. Now get the value of C. It is 1 by 2 pi 6000 into 120, which comes to be around 0.22 microfarad. And then coming to the resonance in parallel RLC circuit. So here this is the circuit. Three branches are connected in parallel. The resistance and the current in the resistance is marked as IR. This is inductance. Inductive reactance is indicated as J omega L. Omega or L is XL, and current in this branch is IL. The capacitance, the current is IC, and capacitive reactance is 1 by J omega C. And V is the applied voltage, and current is I is the current flowing in the circuit. So here we will write the equation for admittance, and from the equation of admittance, if you are going to equate the susceptance to 0, that is this part, we can get the resonant frequency. So try to understand that in parallel RLC circuits, the total susceptance will be 0. So therefore, in parallel circuits, we'll be writing equation for total admittance. So here the total applied voltage will be equal to I into Z. So that is Z is the total impedance of the network. So we also know that Z is equal to 1 by Y. Y is the admittance, reciprocal of impedance. So this can be written as I by Y. Now the admittance can be written as, so that is for this branch it is 1 by R. 1 by R is nothing but G. I am writing G here, plus 1 by J omega L, that is here, and this term it is 1 by J omega C, which will be J omega C. This further can be written as G plus J omega C minus 1 by omega L. So at resonance, that is omega equal to omega R, the net susceptance is 0. So therefore you replace omega by omega R. So this susceptance becomes, this part becomes omega RC minus 1 by omega RL. So equate this to 0. So if you equate this 0, you can get an equation for omega R. This will be equal to 1 by under root LC. So this is the equation for resonant frequency. So this equation and the resonant frequency equation of series RLC circuits are same. At resonant frequency, the total admittance will be equal to G, that is conductance. So conductance G is nothing but 1 by R. So at resonance, please try to understand that the admittance will be equal to 1 by R. That will be equal to the conductance of the circuit. And also the current at resonance will be equal to voltage multiplied by the conductance value. That is I is equal to Vg G is nothing but 1 by R. So therefore we can write current as V by R. So the voltage across the resistance divided by resistance will be the current I. So the current I will be same as that of IR. So at resonance, the current IR or the current flowing through the resistance will be same as current supplied by the source. Then coming to current magnification, which is called as Q factor for the circuit. The Q factor for this circuit is R by omega R into L. It is just inverse of the value that we got for series RLC circuit. So current magnification Q, it's also called as Q factor. It is given by R by omega R into L, which also will be equal to omega R C into R. If you compare this the Q factor of RLC circuit, it is just inverse of that. If we substitute omega R equal to 1 by under root of LC in Q is equal to R by omega R L, that's this part. So we get Q as R into under root of C by L. Bandwidth and half power frequencies. The lowest half power frequency is omega 1 equal to, in this case it is minus 1 by RC plus under the root of 1 by 2 RC whole square plus 1 by LC radians per second. Similarly, the upper half power frequency is omega 2 equal to 1 by 2 RC plus under the root of 1 by 2 RC whole square plus 1 by LC. So here the difference between omega 1 and omega 2 is, in this expression there is a minus sign, here there is no minus sign, and here the bandwidth is given by omega 2 minus omega 1, which will be equal to 1 by RC. So this term corresponds to half of the bandwidth divided by 2. So bandwidth is 1 by RC. So since we have 2 in the denominator, so this is equivalent to bandwidth by 2. So for Q very much greater than 1, this term 1 by 2 RC will be very much less compared to 1 by LC. So therefore this term can be removed from omega 1 and omega 2. So in that case, omega 1 can be written as bandwidth divided by 2 plus omega R. Similarly, omega 2 can be written as bandwidth divided by 2 plus omega R. So here the bandwidth is omega 2 minus omega 1 is nothing but by RC. So relation between Q and bandwidth. So Q is omega R by bandwidth. It's a common expression. And this will be equal to, that is R by omega R L, that will be equal to omega R C into R. For Q very much greater than 1, so we can write omega 1 as omega R minus of the bandwidth, and omega 2 can be written as omega R plus of the bandwidth. These expressions are same as that of the expressions we have used for series RLC circuit. Coming to the practical resonant circuits, it's a practical parallel resonant circuit. Actually, you see only two branches. There is no branch for a resistance separately. So here the resistance Rs is in series with inductance and current IL is flowing, and here capacitance is C. This is another branch connected across the source and current is IC. The total impedance of the circuit is called as YT. This is equal to first branch admittance plus second branch admittance. So first branch admittance is Rs plus J omega L. XL or J omega L is the inductive reactance of the inductance. And then plus for this capacitance it is 1 by minus JXC. Now you multiply and divide this term by R minus JXL. Then we get Rs minus JXL denominator we get rs square plus xl square plus, if you take this j to the numerator, we'll get j by xc. So yt, total admittance, can be written as, so you separate the real part and imaginary part, so we get rs divided by rs square plus xl square plus the imaginary part is j into 1 by xc minus xl by rs square plus xl whole square. So now at resonance omega equal to omega r, the net susceptance will be 0. So equate the susceptance term to 0, that is the imaginary part to 0. And from this you get rs square plus xl square as omega r l into 1 by omega r c. So omega r gets cancelled. So therefore rs square plus xl square can be written as L by C. This further can be written as xl can be written as omega r L. So therefore xl square is omega r whole square into L square. So this term, from this we can find omega r as omega r equal to under the root of 1 by LC minus rs square by L square radians per second. So this is the expression for resonant frequency. And if you want frequency in hertz, so you have to divide this by 2 pi. The admittance at resonance is yt equal to rs by rs square plus xl square. This will be equal to rs into c by L. At resonance, susceptance will be 0 and the total admittance only will be equal to this component, real component. So this further can be written like this. If you are going to replace this rs square plus xl square by L by c, then we get this as this term as rs into c by L. Conclusions. Resonance in parallel RLC circuit. The lowest current from the source occurs only at resonant frequency. Hence this circuit is called as rejector circuit. So this circuit allows lowest current at resonant frequency. Similarly, at resonance, current in the L and C branches can be many times greater than the supply current. Therefore, this circuit is also called as current magnification circuit. And this current magnification is also called as Q factor. At the resonant frequency of the resonant parallel network, the impedance is wholly resistive. The total admittance at resonance will be equal to conductance, and the circuit will behave like a resistive circuit. The value of this impedance is known as the dynamic resistance or dynamic impedance. Summary of the characteristics of resonant RLC circuit. So, a resonant frequency omega. For series resonance circuit, it is 1 by under root LC. Also for parallel RLC circuit, it is under root LC. So Q factor for a series circuit is omega R into L by R, or 1 by omega RC into R. Whereas parallel circuit, it is inverse of this, that is R by omega RL or omega RCL. Bandwidth, in both cases, it is omega R by Q. There also omega R by Q, but Q is different for series and parallel circuits. Half power frequencies omega 1 and omega 2, and it is omega R into under the root of 1 plus 1 by 2q whole square plus minus or plus omega R 2q. Minus sign for omega 1, plus sign for omega 2. So this is the equation is same for half power frequencies for parallel circuit also. For circuits with high Q, that is Q greater than are equal to 10, omega 1 and omega 2 can be written as omega r minus or plus bandwidth divided by 2, and it is same for parallel circuit also. Now coming to the problems, in a parallel RLC circuit shown below, the resistance R is 8 kilo ohm, L is 0.02 millihenry, and capacitance is 8 microfarad. Calculate omega R resonant frequency, Q factor, and bandwidth. B. Find omega 1 and omega 2. And C. Determine the power dissipated at resonant frequency omega 1 and omega 2. So this is a circuit and the supply is 10 sine omega t and I is the supply current. So already we have the formulas. Omega R is 1 by under root LC. Substitute the values, we get this value is 25 kilo radians per second. So the L value is 0.2 millihenry, and whereas capacitance value is 8 microfarad. Then quality factor Q is R by omega R into L. Substitute the values, we'll get Q factor as 1600. And the bandwidth equation is omega R by Q, and its value is 15.625 radians per second. Since the value of Q is very much greater than 1, its value is 1600, omega 1 will be equal to omega R minus bandwidth by 2. So you can use these equations. So that is omega R is 25,000 minus of this bandwidth divided by 2 is 7.812, which gives us 24,992 radians per second. Similarly, omega 2 is omega R plus bandwidth by 2, that is 25,000 plus 7.812 is 25,008 radians per second. And coming to the current and power at omega equal to omega R, we have seen that the total admittance will be equal to 1 by R, or the impedance will be equal to R, which will be equal to 8 kilo ohm. The current will be limited only by the resistance. So current at resonance, it is indicated as I naught, will be equal to V by Z. So that is in the place of Z, we have to substitute the value of R. That is 8 kilo ohm is 8000. So 10 by 8000 is 1.25 milliampere. Since the entire current flows through resistance at resonance, the average power dissipated at resonance is power will be equal to, that is current at resonance is I naught square into R. That is I naught is 1.25 into 10 to the power minus 3 whole square into 8 into 10 to the power 3, which gives us 12.5 milliwatt. At omega to omega 1 and omega 2, so the power will be half of the power drawn at resonance, that is Vm square by 2R. So this will be equal to 6.25 milliwatt. Next problem, a coil of 1 kilo ohm resistance and 0.15 Henry inductance is connected in parallel with a parallel capacitor across a 2 volts 10 kilohertz AC supply as shown in figure. Calculate the capacitance of the capacitor when the supply current is minimum, the effective impedance ZR of the network at resonance, the current supply current at resonance. So this is the given circuit. 2 volts 10 kilowatt supply is applied to this network. C is the variable capacitance and L is 0.15 Henry and the resistance is 1 kilo ohm. So from the given data, you are asked to find the capacitance at which current is minimum. So current will be minimum only at resonance. So let us see how to find this. So FRS for this circuit, it is 1 by 2 pi under root LC. So now try to get an equation for C from this. C will be 1 by 4 pi square L. FR whole square. Now all the values are known. L is 0.15 Henry and FR is 10 kilohertz. So substitute all the values. So you will get C as 1.69 nanofarad. Next, the impedance at resonance will be equal to L by C RS. Already we have seen the expression. So this will be equal to 0.15 is the inductance value, 0.15 henries, and 1.69 10 to the power of minus 9 is the capacitance value we have found out, and RS value is 1000. So this value comes to be around 89 kilo ohms. Coming to the current IS is voltage divided by this impedance. So 2 volts and impedance is 89 kilo ohm, that is 89,000, so which comes to be around 22.5 into the power of minus 6 ampere. Next problem, determine the resonant frequency omega of the circuit shown in figure below. So this is the circuit. Im cos omega t is the current source, 0.1 microfarad, 10 ohm, and in the last branch we have 2 henries and 2 ohms. So for this type of circuit, so we are asked to find out resonant frequency. Suppose if a circuit of this type is given, it's not of standard type, then always you can write the equation for admittance. So the total admittance will be equal to, that is 1 over reactance of this, 1 over resistance, then 1 over the impedance of the branch, that is 1 by j zero point 0.1, that is for this branch, and for this branch it is 1 by 10, for this branch it is 1 by 2 plus j2 omega. So now this can be written as 0.1 plus j omega 0.1 plus 2 minus j omega by 4 plus 4 omega. So you can multiply and divide by a term 2 minus j2 omega for this term. So we're going to multiply 2 minus j2 omega on the numerator and denominator. So we get this term as 2 minus j omega by 4 plus 4 omega. Now you separate the real parts and imaginary parts. So this is the susceptance term. So for the resonance to occur, the net susceptance should be 0. So equate this to 0 and replace omega by omega. Find the value of omega from this equation. We get 2 radians per second. And this is all about the resonance in series and parallel circuits. I hope you have understood the concepts and the problems. Thank you.